Thank you. Welcome, everybody. My name is Saber. I work for TomTom as an application security engineer. Today, I'm not going to talk about vehicle navigation. I'm going to talk about application security. And yeah, so let's take a few steps back and see where this all is coming from. So information security is kind of an old science. So it has its roots from the ancient times. We all know maybe Caesar cipher or vinegar, which was used a very long time ago to encrypt text between different parties. But it has actually been modernized since the Second World War, when Alan Turing broke the Enigma machine and changed the course of history. Going further into network security, now we are more closer into computer science. And we are talking about network, we are talking about trusted devices and external network, public network, now even talking about zero trust network. Going into further, closer to software engineering, we talk about application security. Now we are no longer talking about the organization security or the information or the network. We are talking about the deliverable application or code or web service or mobile application. On the other side, how did companies behave in regard to this topic? Initially, simply denying. Do we need to do anything about security? We just need to focus on software. We deliver the software that satisfies the requirement, functional requirement. But then we noticed that it's not going to work. So we really need to do something. Yeah, what can we do? Let's just blame the developer. The developer needs to take care of security. They need to make secure product. Is that going to work? Of course not. What are we doing next? Yeah, actually, the developers need some kind of a support, some kind of guidelines, OWASP top 10, maybe special publication from NIST 800, and so on and so forth. We have so many documents, so many guidelines, but probably that's still not enough. Next step is trying to make something a bit more structured, which is aligned with the software engineering practices, and we have also some kind of a filter or security gate. Before the release, we have to at least ask a third party to pen test the product to ensure that it doesn't have any major flaws or vulnerabilities or weaknesses that can be exploited. And now we are in an era where we have to automate everything that we do related to security in parallel with the software engineering practice. Let's now move further into software. Actually, software itself, in the meantime, has evolved a lot. We started from centralized development into distributed environment, from monolithic architecture into microservices, and also a lot of companies are now moving into DevOps practices where the developer focuses on the software and the ops team has to focus on the delivery or deployment. All right, before we go to this step, actually, let me ask you one question. If you ever used Yahoo, could you please raise your hand? Okay, not a lot of people. If you ever used LinkedIn, raise your hand. Okay, a few more hands. If you ever used Microsoft or you have an account with Microsoft, also please raise your hand. Okay, so one last name. Let's ask who has an account on Twitter. Yeah, so basically, almost everyone might be impacted by the major breach or data hacks that occurred in the last 5 years, more or less. And you can see that security is not really able to catch up with all the development happening in the industry, and we cannot really prevent this. We cannot really prevent. We try to simply minimize the impact. Okay, now let's try to anticipate what the adversary is doing in order to actually counter it. Let's try to think like an attacker. And from the image, what you can maybe understand what I'm talking about is that the professor in Casa del Papel, he tried to actually think what the other side is trying to do and how can I do to prevent all those defensive techniques. So actually the defensive side need to learn from the offensive side in order to actually do a better job at protecting the assets and protecting the software that we are delivering. And in order to do that, there is an initiative from MITRE Corporation in US, which is called the MITRE Attack Framework. And this framework is actually used and kind of a Wikipedia of all the attack groups or attack techniques and attack tactics in order to make it easier for the defensive team to understand how the attacker behaves, what tactics are used, what techniques are used. The initial version was published in 2018, and it's actually being updated every a few months. I think now we are in version 10, as far as I remember, which last published in 2021 in October. And we have some kind of a set of tactics, and those tactics, each one of them, it has some subset of techniques, and those techniques are actually mapped to specific indicator of compromises, which defensive team can use in order to identify what maybe our adversary is thinking about. Initially, it was published with the enterprise matrice, but there are a few more matrices related to cloud environment, to industrial control system, or also to container and cloud technologies. One more thing that we can do in order to understand better the attackers is actually to reward potential attackers in order to motivate them to tell us about our weaknesses. So we don't need to simply hire one or two attackers or pen testers. We simply open the door for everyone to tell us about the weaknesses of our system. And this was first done by Netscape as early as 1995. So they simply said, it's the first, what we call now, bug bounty program. If you have any weakness that you identified in our system, tell us about it, and we will pay you. This also was adopted by Mozilla Foundation in 2004, but also by bigger corporations like Google and Facebook, which opened the door for platforms like HackerOne, Bugcrowd, SINFO, Cobalt, and Integrity in order to do some kind of matchmaking, bring all the best attackers, crowdsourced set of attackers all around the globe, and give them these specific assets with specific rule, and then we tell them, if you find something, we will reward you, we'll have a better rank, and we'll get you paid. There are a lot of people who are having this as a full-time job. Of course, this is not just pink and flowers and blue sky. There was some limitation on that, especially in the early days, where some attackers simply say, if you want me to tell you about the weakness, you have to pay me first, and so on. But let's skip that discussion. OK, let's now try to think about the difference between the offensive side and the defensive side, and why the defensive side is not doing probably enough to stop completely this attack, which is simply impossible. From one hand, the offensive team basically has to work, offensive team simply are actively scanning for vulnerabilities all around the globe, all around all organizations, trying to find weaknesses here and there. While the defensive team, usually they are bound by working hours. You have to work from 9 to 5, and so on and so forth. We still have some kind of course, on-call engineer, but it's not enough to counter people who are actively 24/7 working all around the globe. Also, the offensive side might not really need to respect the law. People are not necessarily in the same country. They might be in some different region of the world. They don't really care about the law. One more thing is that they don't really need to achieve any exploit during the working hours where people are actively monitoring the network. They might choose to do that during Christmas holiday or during the weekend. And finally, attackers might focus on a specific technology. They are specialized. But as a defense team, that's not always the case. You might have a different set of tech stack that you need to protect. So it's not that easy to defend all of them. While as I said, while the defense team has heterogeneous tech stack. So at the end of the day, attackers only need to succeed once. And the defensive side, it's a continuous battle that the defensive side has to always win. This is not really all the story, but also after the initial access, it's the other way around. Once the attacker achieves the initial access, actually, the first mistake that the attacker will do, he will get caught. So because the defensive team are not putting a single barrier, they are putting multiple barriers. As I mentioned in the tactics and techniques by MITRE attack framework, if someone do something suspicious in the network, then he will get caught. So that's probably the competitive advantage for the defensive team. Now let's talk about soft skills. There are a number of skills that defensive team need to learn, especially from offensive side, but also from the company. So one of them is problem solving, creative problem solving. Software, usually they need to take care of delivering a software that works, but also that they need to take care of quality, they need to take care of user experience. Attackers do not need that. Attackers need to achieve an exploit. They need to compromise an asset. Whether that is done manually, automatically, with good experience, user experience or not, you are not selling this to someone sitting on a bench. Most important is that you achieve your goal. So problem solving is critical, and also analytical thinking is critical for a defensive team. Communication is key. Communication is key because, as a defensive team, you really need to talk with different stakeholders, from C-level to developer to architect to product owner, and sometimes even to external stakeholder. Also, you need to work in teams. We need to work in teams in order to be able to share the knowledge that we all learn, and also in order to be able to improve our product according to the lesson that we learned. And finally, attention to detail and persistence. I think this is relatively obvious for offensive especially, because you might not be able to succeed the first time, the second time, the third time, but you really need to pay attention to a single detail that matters, even sometimes not related to the software at all, simply by relying on open source intelligence, by relying on, I don't know, 0 days or something. As soon as you find the information, you map it to another information, you compose it all together, and then immediately you can create an attack scenario and exploit it immediately. And persistence is key. All right, let's now move to the technical side. A secure software development lifecycle. And the first step in the secure development lifecycle is threat modeling. How can we do threat modeling? According to Adam Shostak is one of the famous people in this industry, and he divided this into a simple approach. 4 key questions that we need to ask. First one is, what are we working on? Is this a mobile application? Is this an online service? Is this an industrial control system? What is the context of our product or service? What is the scope? And what are the assets that we need to protect? Once we understand properly the system, then we ask ourselves the second question. What can go wrong? What can go wrong in a sense like software developers usually are focused on the functional requirement, so they need to make sure that if you provide this input data, you get this output data. If that's satisfied, the software is working well, not from security perspective. Because what if I put a SQL injection? What if I put a malicious content or malicious software in the platform? What can go wrong in a sense like you don't only think as the user as a trusted person who's gonna do what you asked him to do. What if that user itself is an attacker and he will not try to play with your role as a software, he will try to misuse any interface that you have in order to inject malicious content. Third question would be, what are we going to do about it? This is a bit more related to risk management. It could be that you have to improve your product, but the improvement costs a lot of time and money and resources, and the exploit itself is not really relevant, so maybe we are not going to do anything. We just accept the risk. But in other cases, maybe the exploit is super easy to do, but the impact is super big. So we definitely have to take care of that. Finally, we do a retrospective. Did we do a good job? Is that enough? Is this all potential attack scenarios? Did we miss anything? Are we doing enough to deliver this product? Is it good enough? This is actually problematic. But I will come back to this point later. Now let's zoom out a little bit and look at how the secure development lifecycle looks like. So we start with the secure design and architecture phase, and where we just have some kind of requirement, what the product looks like, what the product is expected to do. And then we implement that product, and then we test it, and then we release it. In parallel with each of these steps, we have some kind of security process that we have to do. Each of them triggers a security action. As I mentioned earlier, the threat modeling usually is done at early stage. So we try to talk with developers and ask them these 4 questions and see if there are things that they missed. The good thing about the threat modeling is that it achieves shift left. Shift security left, it means that the earlier you solve a security problem, the less it costs. If you already implement something and then you show it to the security expert and he will tell you, no, this is completely wrong, you have to redo it again. You lost a lot of time and resources and money and so on, so that's not good. Second side is when you commit a new code or when you try to actually make a change to the code, we do some manual activities like code review by security expert, in addition to the code review for functional aspect, but we also have some kind of automated scans, SAST, DUST, SEA. These are some kind of abbreviation related to security tools. SAST means like secure application, static application security testing. DUST is dynamic, and software composition analysis for SCA. So what we want to do is that automate the code review process. So we try to look for functions that could be used in order to do buffer overflow, SQL injection, and so on, and automatically find them, flag them, and ask the developer to do whatever action is necessary to counter this attack. Software composition analysis, on the other hand, is related to the supply chain attack. If you are developing a software, you don't really write everything. You have to rely on third-party library, and those libraries sometimes are written by whatever developers on the other side of the world, and it might not be as secure as our code. So we need to make sure that that dependency is also secure. And then we do the pen testing in order to make sure that, as I mentioned earlier, before the release, we have to test the product and make sure that it is good enough. We do some also fuzzing, or in case of containers, we use the container scan. And during the deployment or the release, we sign the code, and we do also some kind of secret management. If we have KPI infrastructure, we ensure that all the keys are updated on time, and so on. I promised earlier to come back to, did we do a good job? How can we know, did we do a good job? We have to measure it. So if you don't measure it, you can't improve it. And for that purpose, we can use OWASP SAMM, Software Assurance Maturity Model, which is composed of 15 practices elaborated into 5 categories, from governance to design, implementation, verification, and operation. You probably can see some kind of similarity with the previous slide. Secure development lifecycle. So each phase has some kind of related maturity score that we need to ask ourselves certain questions and see if we are doing enough or not. Also, well-architected framework. So this is some kind of a set of guidelines offered by multiple cloud providers like AWS, Azure, and Google Cloud. And it allows us to actually improve our deployment in a sense like we can detect or prevent certain attack. This is not really specific to security, but one of the pillars is related to security. What are all the pillars? First one is reliability. The question we can ask ourselves is how to recover quickly from failure. Second, security, how to protect information and asset and system. Third question is how can we avoid unnecessary cost. When we have cloud deployment, we have multiple instances and services, and sometimes we have some kind of overlap, so we need to optimize our cost. Then, operational excellence, how to automate changes and manage daily operations, especially the manual one, we need to really automate them. And finally, performance efficiency, how to select resources, the type and size optimized for the workload. Now, let's do another retro. Is this good enough? In addition to, of course, the secure development lifecycle, including the threat modeling, manual code review, and all of these kind of security checks here and there and so on, But we mentioned earlier that companies adopting practices like DevOps, they want to develop faster. They don't want people coming to them, hey, wait, you have to check this, you have to update that, and so on. So the question is, from one side, for example, let's take the threat modeling. What are we relying on? We rely on probably documentation. Is the documentation always reflecting the reality? Absolutely not. Is the developer always knowing what the product actually looks like? Not always. So which means we are doing threat modeling based on claims, not on actual facts, which means that our threat model might not always be reflecting the reality. It's not always accurate. Second thing is automation. Yeah, we use automated tools to reduce the manual effort. To reduce code review, we have to use SAST, for example. But still, how much can we automate? These tools, they have false positive and false negative. These tools don't necessarily cover all the technology stacks that we use. So there are always some barriers to automation. A lot of things still need to be done manually, including, for example, pen testing. Coverage. I touched a little bit on this on the previous item. Coverage, especially when you have multiple heterogeneous technology stack and environments, so it's not that easy to cover everything with a single tool. You might have to use different tools and so on. And finally, feedback loop. And this is probably the most important one. How can we prevent developers from doing the same mistake again and again and again? It's not just about training them. It's a bit of wider scope. Security team now, of course, they learn about mistakes because everything goes to the security team. They collect all the incident. The security tool itself is continuously improving. But how can we improve the feedback loop within the organization itself? So yeah, probably security team usually have limited budget, so they cannot really make something 100% secure. But how can we improve with the same budget and do a little better? And that's what's going to bring us to chaos engineering. Chaos engineering is actually not really related to security. It's a bit of older concept, which let me start with a bit of a metaphor. In automotive industry, when OEMs make cars, actually they rely on a set of multiple companies all around the world that are making each of the component. Tires, airbag, I don't know, windshield. Each of these components is actually thoroughly tested. But still, when you assemble them together and you have a car, you cannot just say, OK, we tested everything, so the car is safe to drive. Sorry, it's not how it works. You have to test the car as a whole system. Same goes to software. So actually, we cannot really prevent cars from having accidents, so we need to see how they behave when an accident occurs. So that means chaos engineering, it simply accepts that failure is inevitable, and it will use it as a learning opportunity. What can we improve in order to reduce the impact when it happens? All right, let's ignore this picture for a while, but let's look a bit into history. Chaos engineering was actually invented by Netflix in 2010, and they made it public or open source in 2016. It's available in GitHub. And in 2020, AWS actually added it to the pillar of well-architected framework, which I mentioned a few slides ago. So the idea is actually to improve reliability. The system has to self-heal or self-recover when an incident happens, when a service goes down. Let's take this infrastructure as an example. So you have multiple availability zones, you have an elastic load balancing, and you have multiple instances. So the elastic load balancer is trying to reroute traffic depending on the load, and what we can see is that this instance was killed. What would happen? The elastic load balancer should actually behave accordingly. This instance is no longer available. The health check shows that the instance was killed. So we need to reroute as much traffic as possible to the other availability zone. And in the meantime, take whatever action necessary in order to reinstantiate that instance. OK, so how does this work? The idea is to actually start from a steady phase. And from the steady phase, we have a system that works. We have service level agreement, we need to commit. We commit to the customer that the service will be available 99% of the time or more. And then we try to take an hypothesis. This hypothesis, like I mentioned earlier, simply an instance is killed, how the entire infrastructure will behave, how the entire infrastructure will recover from this incident. We don't need to have an on-call engineer in order to manually do the job. The whole system needs to automatically recover from this incident. So we ran the experiment, and we see. We made an assumption that the system will recover, but is that the truth? So then, after we ran the experiment, we probably noticed that most cases, yes, it is the case, but in some cases, maybe something would go wrong, and the system will be stuck into a state, and that instance will never be run again. So we verify the assumption, we improve, and we go back, and we repeat. So that's probably not related to security, as I said. So how can we make it relevant for security? It's more about the hypothesis. Now, we took a scenario where we are talking about availability and reliability, but if the hypothesis itself is specific to security, then we can use chaos engineering in security. OK, awesome. I can recommend this book/report, and I'm taking some of the scenarios that I mentioned here. For example, I mentioned earlier SaaS tools that are used to scan the code commit whenever they're committed to the version management system. So if someone, if that tool is out, is down, I mean, it's not available, is the commit still going to go through? Is it going to be approved? And is that code going to be scanned again in the next time or not? So those are some kind of assumptions that we make, but we never tested. So it's good to test them. Another case, let's have a heavy processing application and put them in CI server. So this server is supposed to simply, like Jenkins or so, like you have to build a system and so on. But it's supposed to have certain processing performance, and you notice that something is not behaving as we expected. So if we take this experiment and we see, are we doing something in order to detect how different systems in our infrastructure behave? And then, if we even notice that something is going wrong, and how can we fix it? Another example would be, let's try to commit secrets or credentials or password directly in the source code. This is not a good practice, but at what stage this is going to be detected? Is it going to be detected by the SAST, or is it going to be maybe someone in the code review will ask? No, we should not do that. Another scenario will be, let's just try to inject a dummy image in the image registry. So this is more specific to container technology, and you have a elastic container registry, and that you rely on it in order to build your images. So if that container registry include a dummy image, anybody is going to ask question, or do we have any tool that would rely on, that would detect certain vulnerability in that dummy image? And one more thing is not very different. Let's use or import packages with known vulnerabilities. Is the SCA doing enough good job to detect that known vulnerability or not? One last thing is, like, let's try to run the image into a root service. So as a root, so with high privilege. It's not a good practice, but sometimes people do it. So who is going to notice that this is happening? So these are some of the examples, but of course your creativity is the roof. Now, one more, not one, many other benefit of security chaos engineering is that in the traditional approach, the security team usually work in silo, but with the security chaos engineering, you are actually forcing the security team to collaborate with the ops team and with the developer in order to find this kind of hypothesis and run the experiment. The experiment, everyone is involved in the experiment, everyone will learn from it. Also, in the traditional approach, security is known as the department of no. We never approve anything. Don't do this, don't do that. So people are more scared to even talk to security people. But in the security chaos engineering, we actually incentivize collaboration, and we also incentivize experimentation. And yeah, as I mentioned, so we try to avoid the culture of fear and mistrust. And And that's why in the security chaos engineering, we actually try to create a culture of continuous learning. We all learn. We just don't have to learn simply by reading a book or watching a video, but we learn by doing the experiment, and we see what we have. We understand our own system. Finally, using policies and control to prevent failure is probably not the best thing to do. We still need these policies. We're not saying like we're going to get rid of them, but it's not relying on the policies to simply blame people. You should not do that, or you should not do this. Instead, we just have we use experimentation and transparent feedback loops to minimize failure, the impact of a failure, instead of avoiding the failure. The failure is there. It will occur sooner or late. Maybe it will occur during holiday or when your on-call engineer is not probably able to take the task. So at least let's uncover these weaknesses earlier, and we uncover them in a controlled environment, and we try to improve them, improve our system, and prevent this from happening when we are not ready for it. So people, even in psychological side, they are more used to handling incident instead of focusing on keeping our system up, and when the system is down, we don't know what to do. We have to ask questions, who is responsible for what, and so on and so forth. That's basically it. So I have provided a set of references, so these are useful, including, for example, the MITRE attack framework, the well-architected framework from different cloud providers, security chaos engineering. And it's time for your questions. Yeah. Oops. Take care.
Hello. So you mentioned that security chaos engineering tries to minimize the failures in our system.
Sorry, I don't hear you.
Hello?
Yeah.
Okay. You mentioned that security chaos engineering tries to minimize failures instead of preventing them.
Yeah.
But imagine that someone tries to take advantage of that and makes a big attack that makes the system unavailable for several days. Do you think that in softwares we should make a hybrid approach? So using security chaos engineering and at the same time trying to prevent an attack, or do you suggest an alternative?
Absolutely. So security chaos engineering is not an alternative. Maybe the last table was a bit misleading, but the idea is more of a complement. So we still have to do threat modeling. We still have to do automated scans. We are not getting rid of all of that. Definitely not. That's not going to happen. But what we are trying to do is a complement to all of that, is not to simply shift left and try to solve problem as early as possible and then assume, like I mentioned in the metaphor with the car, that the car is ready. It will never crash. No, no, no. One side, we still do that all checks early in the process. We try to fix things as early as possible, but we still have to test the final deliverable. We still have to make assumption, not necessarily because pen testers, what they do usually is that they have to find one single weakness on the attack surface, exploit it, and then go further. As I mentioned, the MITRE attack framework, one step at a time. But what we cannot uncover is that if the attack surface is relatively well protected and there are weaknesses inside the system, we will never be able to see them simply by pen testing the whole system. So what we need to do is make hypotheses and then try to open doors so that we can check inside the system if there are things that can go wrong after the initial access. So it's more of a complement.
Thank you.
Thank you.
Any further questions?
What was your biggest challenge incorporating security chaos engineering into TomTom?
Actually, yeah. So we are not really talking on behalf of TomTom maybe, but what I would say is that some of the challenge is, as I mentioned earlier, if you have different tech stacks, you have different technologies, so you cannot really have one single process for every team. You have legacy product and new product, you have simply code that is running with C, C++, Java, mobile, API, and so on. So I would say probably that is one of the most challenging. So